Hi, and welcome back to Stats Online. Today's topic is the sampling distribution for the proportion. And the sample proportion is what we denote as p bar, okay? And p bar is very simply x over n, x being the number of successes, let's say the event of interest to the statistician, over little n, the sample size. So if we're talking about the proportion of females in a class, x is the number of females, and little n is the size of the class. So where this is going to play out into a distribution of sample proportions is, here's the thought exercise. For a given sample size n, little n, imagine that I draw all unique possible samples of size n from a population, whatever that is, okay? And each time I do that, I calculate p bar, my sample statistic. If I organized all of those p bars, right, and there could be hundreds of millions of these p bars, then what we want to locate in this particular lesson is what the shape of that distribution is, where the center is, what's the expected value of the mean, and what's the measure of variability in our choices, the variance and the standard deviation. Okay, so we want to know those three characteristics for the sampling distribution for the proportion. All right. We'll start with the first one, which is the shape. And lo and behold, the shape of this distribution can be approximated as normal, okay, which is nice because we have the z distribution. We can find areas under these the normal curve. It can be safely approximated as normal if these two conditions hold. And we've seen these two conditions before with the description of the binomial distribution. N times pi, n times that probability of a success, okay, whatever the success is 10 or more, and n times the probability of a failure being 10 or more, okay, the probability of a failure sometimes being labeled as q. And in cases where pi is unknown, and this holds for this lesson and throughout, we use p bar in place of pi. So we actually use that sample proportion to determine whether the distribution of sample proportions would be normal. And you can think of this rule as the counterpart to the central limit theorem, which of course the central limit theorem applies to the mean. This two-part test that is on the slide applies to proportions. But if both or either, if either condition is satisfied depending on the realm you're in, we can approximate these things as normal. So the population proportion for students who brought video game schools to school with them is 0.306. So this 0.306 is the pi, that's the population proportion. Can we assume the sampling distribution for the sample proportion is normally distributed if a sample of 15 individuals is selected? And the answer here is no. And the reason is if we try to satisfy these two conditions, if we look at n times pi, which is 15 times 0.306, we get 4.59. And of course, 4.59 is less than 10, and so we can't safely assume that this distribution of sample proportions would be normal. So the answer is no there. The sampling error for proportions. So toward describing both the expected value of the mean and the variance, let's introduce the definition for the sampling error, which again is p bar minus pi. So the sampling error is always a sample statistic minus, or you're subtracting the sample statistic from the population parameter. So it's that deviation between the two. And here it's p bar and pi. Okay. Now, although p bar is going to differ depending on what your sample is, right? Sampling error just means exactly that you're pulling from the population. You don't have the population as a whole. And so you would expect that the statistic differs from the parameter value. However, one property of the sampling distribution is that if you repeatedly sample, on average, your average p bar will equal pi, will equal that probability of a success, the population parameter. So it's an unbiased estimator. Just like x bar is an unbiased estimator of mu, p bar is an unbiased estimator of pi. When the sampling distribution can be considered normal, so if those two conditions are held, and we have that the fact that on average p bar equals pi, the standard deviation, aka the standard error of this distribution, follows this formula. Okay, sigma sub p bar equals the square root of pi times the probability of success times the probability of failure over n. All right. Now we can take all of these properties and recognize that, okay, if it's a normal distribution, we have the center, we have the spread here, the standard error, and we have the shape. We know if it's a normal distribution, we can use the z-table, and the following formula will allow us to calculate those z-scores. P bar minus pi in the numerator, that's the deviation from the mean, and the standard deviation, the standard error in the denominator. The steps to finding a probability, okay, associated with the sampling distribution for proportion. Step one, you're given a population proportion pi. All right, it could be the case that you'd have to calculate it, or in the sense that I'd say, it's the likelihood of getting a 2 on a roll of a die. Okay, so then you're talking about 1 out of 6 chances, and that would be pi. But for all intents and purposes, you're given pi. You need to calculate your sample proportion p bar, okay, for a particular sample, and then determine the mean and standard error for the sampling distribution. All right, following those previous formulas. And if the distribution can be assumed normal, the two-part test is satisfied, then we can calculate our z-scores and use the z-table. All right. So here's the practice problem I want to go over to get practice with this. Based on past experience, 20% of contacts made by a firm's sales rep resulted in a sale being made. Okay, so 20% is going to be the historic probability percentage, and we're going to use that as our population probability of a success, 0.2. Now, last week, Charlie, potentially a slacker, claimed that he contacted 100 potential customers and only made 10 sales. All right, so 10 of those 100 turned into a sale. So given a random sample size of 100, right? So think about it this way. Given a random sample size of 100 like Charlie's, what's the probability of getting a sample proportion of this size or smaller, of 10 or less? All right. And so I want to finish up this lesson by going over that, an example like this. All right, so we have the elements, the important elements of the problem was pi was 0.2. That was the 0.2 was the population probability there of making a sale. The sample was 100, and the sample proportion was Charlie's 10 over his 100 calls, which is 0.1. Okay, we know that this is going to be normal because n times pi equals 20, and so that satisfies the conditions. My axis is p bar. The center of that is the expected value, okay, which is 0.2. The remember, on average, p bar equals pi. The standard deviation again is 0.2 times 0.8 over 100, and the square root of all that, and it's 0.04. Right, so if we're going a couple standard deviations around the mean, we're going to have a normal distribution that looks like this. And what we are trying to figure out is what's the probability, okay, of 0.1, the sample proportion that Charlie got, right, 10 out of 100 calls or less occurring from this sample size, this area in red, all right? And the step that we need to, kind of the second to last step here, is calculate what that z is, right? This is a normal distribution, and this z is going to be 0.1 Charlie's proportion over the population minus the population proportion divided by the standard error, and that's negative 2.5. Okay, so if we go to negative 2.5 on the z table, you should be able to figure out or locate the probability 0.0062. So 0.6% of the time, okay, would 100 calls result in such in 10 sales or fewer. All right, and so that may be enough evidence to consider Charlie potentially slacking on his cold calls and not just attributed to random chance.